All right, so let's take a look at some of these Linux exploits. And for this, you want to use an Intel-based machine. I just wrote the projects assuming you're using an Intel-based machine. And you can do some of this on an ARM-based machine, but when we get to injecting shellcode, it won't work on an ARM-based machine. So I've got a Intel-based machine running here in the UTM environment, uname minus A. So it's actually running on ARM processor, but it is emulating AMD 64. And so you can install GCC Multilib, which I've already done, which lets you compile 32-bit code and run it on a 64-bit machine. And I always start my students with 32-bit code because it's simpler, and then they move up to Intel 64 and then ARM after that. So the first program we're going to use is this one here called buff. And what this does is it has a main routine that asks you for your name and reads it into a variable up to 200 characters long, and then calls this buffer overflow subroutine with that variable name and another variable which contains a Linux command date. And those two variables are only 40 characters long here, and it copies the incoming command and name into local variables and then executes the command as a command. So this is an artificial situation where strings you type in can be interpreted as a command and executed, just like the other command injections that we played with. So if I do buff 32 and I give it a name like AA, then everything's fine. It says goodbye AA and executes the command date. And here it tells you the name is stored at location AFE0 and the command is stored at B008. So the difference between them is F0, this is 32 plus 8. This is 40 bytes further along than there. So if you put in 40 letters followed by a command like this, then you'll have command execution. So I put in 40 characters and then ls, and now the command that executed is ls. So I can execute as many commands as I want. The simplest way to do it is just do a semicolon and pack them in here. So I can do who am I, and then ifconfig, and any other commands I might want to do. It'll execute them, except that this server doesn't have ifconfig. It did who am I. I think if I want to do it, I'd have to do IPA. And that, but let's just try to do an ls minus L. That'll be enough. If I do ls space minus L, then it does an ls, but it doesn't do an ls space minus L because the space terminated this string and it wasn't read in as part of the first string to be there. So you have to find some way to conceal that. And on different systems, it takes different tricks to do this. Sometimes backslash space will work. In this case, it won't. Um, Another thing that works sometimes is $IFS for inter frame separator and then minus L. That's a environment variable that serves as a separator like a space. And in this case, that one works. Sometimes you can do it with quotes in different environments, but not in this one. So, you just have to try the different options to find out which one is going to work. And so after you be able to see how this runs locally, you can then exploit it on my server. I've got a server here with flags hidden on it, and you have to use command line commands to get there. So this is the simplest case of buffer overflow, where you overflow from one variable into another variable, like I showed you in the Rust demonstration. This is not the most common buffer overflow, or the most powerful, but it is the one that is hardest to stop. Even all the modern buffer overflow defenses, um, like address space layout randomization, data execution prevention, stack canaries, just to detect when you're overflowing the stack, none of those will stop this kind of overflow. I'm not aware of any defense that will actually stop this kind of overflow in any modern operating system. All right, so now we can do another kind of overflow. We're going to use a 32-bit program, which is this one. All right, so here I've got a main routine that calls test password to decide whether you entered the right password. And here's test password. It lets you enter a password. It only reserves enough room for 10 characters, but it lets you put in a password up to 50 characters. And then, no matter what the password is, it always returns one saying you had the wrong password. There is no correct password, so there's no way to execute this win function. That the developer wrote a program where they did not intend for you to be able to ever get to this win function because this condition will always be true. But we're going to get there by exploiting an overflow. So let me get the instructions on another screen so I can see them more easily. All right. Now, one issue is if I run this thing, PWD, and I give it, oops, it's PWD 32 is what it is after I compile it and make 32-bit code. Okay, if I give it a password of 1, it says I fail, of course, and it prints the address where the password is stored. Now, if I run it again, I get a different address. Notice FBB, FBFC. Every time I run it, I'm going to get a different address because address space layout randomization is in effect on this machine, and that is going to follow up my exploit. My exploit is a simple one that dates from a time before that. So to make it work, I have to turn that off. And you do it this way, sudo su minus to become root. And now you adjust an environment variable called randomize VA space. This is a system variable. You put a 0 in there, and that will turn this off. So now when I go back to my normal user, and I run this program and give it a 1, and run it again and give it a 1, and run it again and give it a 1, now the storage address is always the same. So this is what you need for this simple attack to work. When you reboot the machine, it'll automatically turn the randomization back on. All right, so we've now let's look at the, all right. See, I was looking at the wrong series of instructions there, but that's all right. All right, the same thing is true. Okay, so now let's try exploiting this program, PWD32. If I give it a password of just one character, it just says fail. But if I give it a long password, then I get a segmentation fault. So this is what you usually see indicating to you, just like that SQL injection syntax error, this means somehow I have caused it to reference an address that is not reserved for this program to use. So to understand more of why that happens, you have to debug the program, and the GNU debugger is the standard and the best in my opinion. So this will debug that program, and the -Q just makes it in quiet mode so it doesn't bother showing a decorative banner. And in this case, since I compiled the program with the -G switch, I can do source code debugging, which makes it easier. So I can list the source code of the program here. Here's the first 13 lines. And so here you see, this is the routine that tests the password. This is the command where the overflow happens, where it reads data from the input that can be longer than the space it allocated for the password. So I would like to put a breakpoint after that overflow, putting a breakpoint at line 9. So it'll run only to that point, and then before it tries to return, I can examine the structure of the stack. So now we'll do normal execution of the program, and here I'll put in 8 A's, which is going to fit into 10 characters without overflowing. So here I'm at the overflow. So now I've stopped at that point where the overflow would appear, so I can look at the registers. And if I look at the registers, the main thing to notice is the stack and base pointer here. When you enter a subroutine, you set aside a certain room on the stack to be used for local variables within that subroutine. And when you return back to the calling program. And the stack frame for this subroutine goes from ESP to EBP. So it goes from B0 to C8. So I can examine the stack with X slash, say, 8X, or I guess 12X is all right, of ESP. And there's the stack. And you can see, here's the A's I put in. 41 is the number for A, the ASCII character. So here's the A's. And because it's little endian, it's out of order. So these are the first 2 A's. These are the next four A's, and these are the last of my 8 A's. So there's all the A's. Here's the carriage return at the end and a null byte to terminate it. That's the stuff I entered. All right. And EBP is FF4C8. So this is right here is EBP. And the next word after that, so the stack frame goes from here to here, including 7 32-bit words. That's the storage area reserved for this routine. And when it's done, it will return to this address, 5655. And you can see my instruction pointer is right now at a 5655 address in test PW. And this is the 5655, 6255. That's the address of the next line of the main routine. And I can see that by disassembling main. All right. And so here is where it calls test PW. And here's where its return is 5655, 6255. And that's this number. So this is the return pointer telling it where to go when it's done executing the subroutine here. And as you can see, if I overflow the stack enough, I can change that address and cause it to go to a different address when it returns. So let's quit from this. And now let's overflow the stack. So run and say yes. Now I put in a long password with a lot of A's in it. And now when I do info registers, I'll see the same thing I've been talked about many times here. The problem with C is that when you put in a large block of data, it does not change the amount of storage available for it. That's the flaw. So the stack frame still goes only from B0 to C8, even though that's not big enough. So if I look at the data near the stack pointer, now I have all these 41s going everywhere. The stack frame ends at C8. So this is the stack frame. This is the return pointer, and I've overridden the return pointer with some of those capital A's. So now if I continue running the program, it's going to crash because it's going to put this 41, 41, 41, 41 in the EIP, and that is not an address available for this program to use. Info registers shows that the instruction pointer now contains this invalid value, and therefore the program crashes. So all I know now is some of those letters end up in there. If I want to know which letters really ended up in there, then I have to run it again and now put in a non-repeating pattern of characters. Like this here, 4A's, 4B's, and so on, up to the I's and J's. Now, if I examine this, the registers are going to show the same thing. The stack frame goes from B0 to C8. And if I examine the stack, C8 is here. And so the 46, 46, 47, 47 is what ended up in the instruction pointer. And so A is 1, so it's A, B, C, D, E, F. 40, that's FF. These are the first two F's and the first two G's in that string. So now I know what to put in there, and I can put any address I want by replacing those 4 characters with the 4-byte address of any address I want. And of course, I want to run that win function. So I disassemble win, and I can see the address where win starts. So I'm just going to copy that address and put it in the clipboard. And then I'm going to make a Python exploit that will attack this server. So I nano exploit pwd32. Okay, and now first thing I'm going to do is put in the thing in my clipboard so I don't lose it. That's the desired address. This is where win is. And now I'm going to put in my code here from my example. All right, to get going. And you can see this is a common thing. This is what is my example, but every machine is different. The layout of the operating system and versions and stuff matters. So I'm going to copy that line and put it up here and get rid of this old one, which is not quite right. This is the most common mistake my students make. They run my example code exactly as it is, and it's different address on each machine. So here's all that input up to the 2 F's. Then I have two Fs and two Gs, which are going to be 4 bytes I specify here. And then this is a best practice. Always keep the length of your attack the same. This particular program is so simple that you don't have to do that. But when you go to exploit a Windows program, we're going to see that longer injections can actually crash at a different point in the code. So if you're going to exploit a particular injection, you want to keep the length fixed. So I carefully filled it in to keep the length fixed. And here's where the address I want to go to goes in reverse order because of little endian. So I want to go to 5655, 62 OB. So this should be 62, and this should be 0B. There. And if I've done everything right, this will run the win function. So I can chmod plus X to make it executable, exploit. Okay, and then I can test it. If I just run it, it's going to print this junk on the screen, FF, then come 4 characters before the GG, and some of them are not printable. So it might make more sense to put the output in, say, a file like foo, and then I could examine it with XXD to see how it looks. Now I see, here's the address, 565562 0B in the middle. And the 0B is something like a form feed or something, some unprintable character. So I can run this and feed the input into /pwd32. All right, that didn't do what I expected. Oh, I know why, because I have to do it this way. It's input that you put in after the program is running. It's not a command line argument. So you have to do this and take it from this. This should work, and if not, I'll check my instructions to find out the right syntax. But that should run it and feed it into there. And still doesn't work, so let me just check my instructions and get the right setup for it. You can do it in the debugger. Let's try that. If I run my GDB again, PWD32, and then I can put the break at 9. This is good to see if it's going to work. Wait, what? All right, something weird is going on here. Let me quit from here, do an ls. I have it is PWD32. Oh, well, that's interesting. Oh, I wiped it out somehow. Ah, I made a mistake somewhere. I put the output in there and destroyed it. I have to recompile the program. Okay, fair enough. I wrote into there instead of running it. All right. Here's the command that compiles it. Okay. There we go. Now I have PWD 32. Okay. All right. Now let's put it in the debugger again. All right. And now I can run. Let me get to my instructions to make sure I'm on track here. All right, run with --args. And I want to take it from that output file foo that contains the text of my exploit. So it's going to run, and see, I win with you win here. So I know it worked. But if I want to see exactly how it worked, I can put that breakpoint back in and then run it again. Say yes. Now it's going to stop at the breakpoint. So if I do info registers, I'll see that the stack goes from B0 to C8. And if I examine the contents of the stack, B0 to C8 is here. And here's the address 565562 0B. And so if I take one more step, then I executed that command. And next, now I'm in win. So it went into their bracket and it went into win. And so if I continue, it's going to print the win message. And then it's going to crash because even though I changed the instruction pointer to go into win, I didn't fix the saved base pointer. So there are some corruptions in the registers that are eventually going to make it crash. I could write a more careful exploit, but this is good enough. And by the way, the debugger is not a perfect environment to test things in. Sometimes addresses are a little different. So sometimes when you make an exploit that works in the debugger, it doesn't work in the actual command line. So you might have to test it both places. I think this one will work. If I take it from foo, yeah, it does work here. I get the UN message and then it crashes. So anyway, that's what I wanted to show you. That's the simplest exploit where all we did was feed in an address and redirect execution to code that was already there. And even though this is not the most powerful, this is again very useful and very commonly done because it's a way to work around address space layout randomization. It's a way to, if you cannot inject code and run it, which is data execution prevention, then you can use this technique to reuse code that the developer put there. And that's called a trampoline attack or return-oriented programming, where instead of injecting code, you just inject a series of addresses that run snippets of code that are already in the system. And you piece together your exploit like making a ransom note by cutting words out of the newspaper. So anyway, that's all I wanted to show you for now. We'll do the rest after lunch.